Okay, now we will discuss the working principle of DC motor. So when I say DC motor, it is the one which is going to take electrical power as input and gives mechanical power as output. So here in this case, we are going to discuss about a two-pole DC motor. And when the DC motor is connected to an external source of DC supply, the field coils will be excited and they will be developing alternate south and north poles, and also the current is going to flow through the armature windings, right? Now if you consider all the armature conductors under n pole, that is north pole, carrying current in one direction, let us say it is into the plane of the paper, then all the conductors under the south pole will be carrying the current in opposite direction, so that will be out of the plane of the paper. So as each conductor carrying a current and is placed in a magnetic field, it will experience a mechanical force, right? This is because here the armature conductors which are carrying current will also act as electromagnets, and due to the continuous repulsion and attraction between those magnetic poles, the entire rotor will be rotating in one direction. So in order to determine this direction of force or rotation, we are going to use Fleming's left hand rule. So now we will see what it is. So in case of Fleming's left hand rule, uh, if you remember, we used Fleming's right hand rule for getting the induced EMF or current direction in case of DC generator. So here, in order to get the force direction, that is rotor rotation direction, we are going to use Fleming's left hand rule in case of DC motor, right? So as per this rule, if we arrange our thumb, forefinger and middle finger of the left hand perpendicular to each other, then the thumb points towards the direction of the force experienced by the conductor, when the forefinger points towards the direction of magnetic field and middle finger points towards the direction of electrical current. So this is how we are going to determine the force direction, right? Next, and if you see, by applying this Fleming's left hand rule in this case for this motor, since all the conductors under the north pole are carrying current into the plane of the paper, and the dot symbolized conductors which are under south pole are carrying the current in out of the plane paper, that is out of the plane of the paper, right? So that means if you observe this Fleming's left hand rule, the rotation you will get is anti-clockwise. So that means the force on each conductor is tending to move the armature in anti-clockwise direction. So the force on all the conductors will be adding together to experience a torque, and which makes the armature to be rotating, right? When the conductor moves from one side of a brush to the other side, the current in the conductor is reversed, and at the same time it comes under the influence of the next pole of opposite polar. Due to this action, we are going to experience the direction in one direction, like in one side only. So the motor will be rotating in the same direction because of these brushes as well as with the combination of commutator. So here there is one more parameter which is very important to discuss while understanding the principle of operation of DC motor, that is back EMF. So here this is back EMF because it is going to oppose the applied voltage of the DC motor. That means this is EMF, right? So it is induced EMF, electromagnetic force. We all know, as per Faraday's law, whenever there is relative change in magnetic field as well as the conductor, we are going to get an induced EMF across the conductor. It can be either due to the rotation of winding or due to the time varying nature of the flux. It can be due to anything. So when the armature of a motor is rotating, the conductors are also cutting the magnetic flux lines, and hence we are going to get an EMF induced in the armature conductors. This is as per Faraday's law. So, and the direction of this induced EMF is such that it opposes the armature current. Okay, and the circuit diagram we can see here, which indicates that this is the applied voltage for the DC motor, and across the rotor we are having the armature winding. So the armature winding induced EMF will be back EMF, which is indicated with EB there, and the field winding is carrying the current of IF, and armature winding current is given as IJ. Right now, that is induced EMF across the armature winding, and we all know the mathematical expression of that induced EMF, which is same as that of the generating principle. There we already discussed about it, and the same expression will be valid here, right? But coming to the DC motor, we need to get equation of torque, because that is the main output of the DC motor. And in order to establish the equation of the torque, we need to consider the power first of all. So power means here the output power is mechanical power, and if you consider the losses are neglected here, output mechanical power will be equal to the input electrical power. So electrical power, since if we neglect the losses, there won't be the presence of RA here. That means the effect of armature resistance will not be there. That means what we will have, the mechanical power output will be equal to the product of EB and IK, that is voltage or power coming out of the armature winding, right? So back EMF is the one voltage across the armature winding, and IA is the current flowing through the armature winding. So its product will be mechanical power output. And we also have the equation of mechanical power with respect to the torque and speed of the rotor. That is given as product of torque and omega. Omega is nothing but the speed in radians per second. The units are very important here. And if you equate these two equations, you will get EBIA is equal to TG omega. Right? And now if you simplify the torque equation by substituting EB is equal to P pi Zn by 60A, what you will get? You will get torque as given here, which is Pz pi Ia by 2 pi A. So if you note here, we have also substituted omega is equal to 2 pi n by 60, because n is in radians per minute, sorry, revolution per minute, whereas omega is in radians per second. So with that relation, if you substitute omega as well as EB in equation of 4, you will get this TG value, right? And this is the electromagnetic torque of DC motor that we obtain. And we can further simplify this equation by substituting all constants with one constant variable considered as Ka. So here if you see in this expression of torque, number of poles, number of conductors, as well as number of parallel paths, and this 2 pi term all are constant. So we can replace that constant with a single constant, that is Ka. So the Tg torque will be equal to Ka pi Ia. So from this you can say that electromagnetic torque is directly proportional to the product of flux and armature current. Right? This is all about the electromagnetic torque equation of the DC motor, and also principle of operation of DC motor. That's it. Thank you.